So we were talking about root systems, and we will continue to talk about them today. And so let me quickly remind you what we said a root system was. We said that it was a set of vectors in a vector space V. Well, maybe before I come to this, here V is going to be a finite dimensional real vector space that has a symmetric inner product. That might be a strange inner product, but we know it's symmetric. We talked about how if you have some vector in the vector space such that its length is positive, or as long as its length is not 0, you can do this. As long as alpha comma alpha is not 0, you can define for alpha in the vector space, you can define a reflection, sigma alpha, which takes V into this expression. We saw that if this is a Euclidean norm, then this is really the usual reflection, okay? And we talked about properties of this. So two properties are that this is an involution, so that the reflection squared is 1, and it preserves lengths, okay? So given this, I said that our root system was a set of vectors in V, which we call the roots, together with a subset of them called the simple roots that have the following properties. First of all, simple roots have positive inner product with themselves. The simple roots are linearly independent. The only way that you can have two roots that are multiples of each other is if one is the negative of the other. Now, these reflections, sigma alpha, as alpha ranges over the simple roots, they generate a group W, a group of reflections, and when you let the reflections act on the simple roots, you get all the roots. Okay. And finally, any root has to be either a non-negative combination of the simple roots or a non-positive combination of the simple roots. So when we have a setup like this, we call this a root system. Okay? And given a root system like this, we're going to get a group W that I already defined with a set of generators, which is implicit here. Okay? So W is, well, I already wrote what W is, and S is this set of generators. Okay? And my goal for today is to prove to you that if you start with any root system and you define this group with this set of generators, then what you're going to get here is a Coxeter group. Okay? And this will be the way back, because we showed that given a Coxeter group, you get a root system, and now we're going to show the opposite direction. Okay? So this is my plan for today. Let's see if we get there. And so let me start by talking about some linear algebra. Let's say that you take some linear function in V, invertible linear function, which preserves the norm. Okay. And let's say that you take two vectors in V, which are non-isotropic, which remember just means that the inner product with themselves is not 0. Okay? So here's some things we're going to show. These are just some useful linear algebra lemmas. If we conjugate the reflection sigma alpha by this linear transformation phi, then what we get is a reflection, and this reflection is with respect to wherever phi takes alpha. That's the first thing. The second thing is that if you have sigma alpha and sigma beta equal to each other, if alpha and beta generate the same reflection, then the only reason that can happen is because alpha and beta are multiples of each other. Okay. Now, this direction is clear, but this direction is maybe not so clear because we don't know what properties this strange inner product might have. Okay. And finally, sigma alpha and sigma beta commute if and only if. Again, there's two ways in which these could commute. One way is if they're the same thing. Okay. And the other way, we might know what to expect from regular geometry, from Euclidean geometry. Two reflections commute if they're orthogonal to each other, basically. And so this is also what happens here. Okay. So this is what I'm going to show now. Some proofs. These are just some kind of computations that we have to do. So for example, let's do the first one. Let's see what phi sigma alpha phi inverse does to some vector v. Okay. Now, what can I do here? Well, I don't really know much about phi, but I know what sigma alpha is. And so let me substitute what sigma alpha does. What sigma alpha does is that it takes phi inverse of v minus this expression over there. 2 times the inner product of alpha and phi inverse of v divided by alpha comma alpha and alpha. Right? So that's what I get. And now let me compute what this is. Phi of phi inverse of v is just v minus. Now let me keep these inner products. Let me leave this alone and just, this is some number, right? And phi is linear, so I can move phi and make it act here on phi of alpha. Okay? So I haven't really done anything except for bring the phi in. Now I'm going to do something else, which is say that I know that phi preserves the inner product. And I want to use that property to make phi act on the left and on the right here. Okay? So instead of alpha phi inverse of v, I'm going to take phi of alpha and v. Okay? And in the bottom also, instead of alpha comma alpha, I'm going to take phi of alpha comma phi of alpha. And that doesn't change anything. Okay? And now if you look at what this expression is, this is exactly the expression for the reflection with respect to phi of alpha. So this is the reflection with respect to phi of alpha of v, which is what I wanted to show. So this is just kind of a computation. Okay? So that proves A. Let's prove B. So, like I said, the direction from right to left is easy. If alpha and beta are multiples of each other, then it's pretty straightforward to figure out that sigma alpha and sigma beta are the same. So let's suppose that sigma alpha is equal to sigma beta. Okay. Now, let me come over here and look at the definition for what these things are. When I consider sigma alpha and sigma beta, I'm going to find that this v is going to be the same in both cases. And so what that means is that this piece right here has to be the same whether I put alpha or beta. So that means that 2 inner product of v comma alpha divided by alpha alpha times alpha equals 2 inner product of v comma beta divided by beta 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 for all v. And I look at this and I say, well, look, this is a number, this is a number. Okay? I'm trying to prove that alpha is a multiple of beta. I get that a number times alpha is equal to a number times beta. So the only thing that I could be missing is that maybe these numbers are always 0. But is that possible? It's not, because this is true for any v. Okay? So I could just pick any value of v to make sure that this is not 0. And then I'm going to get that alpha is equal to some multiple of beta. For example, I could put v equals alpha in here. If I put v equals alpha, then what I get is alpha equals 2 times alpha comma beta, beta comma beta, beta. So there you have it. Okay. So that's easy. And now let's prove C. Sigma alpha and sigma beta, when do those commute? Well, you could try to do something clever, or you could just compute, because you know exactly what sigma alpha does and what sigma beta does, and you can just plug in. Okay? And when you plug in, I'm going to tell you what you get. You get v minus 2 times v alpha divided by alpha 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 minus 2 v beta divided by beta 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 plus 4 v beta alpha beta alpha alpha beta beta alpha. You just do it. Okay, this is what you get. So let's take our time and parse what this expression looks like. I mean, it's kind of big, but it's not too bad, because you see, we're looking at sigma alpha, sigma beta. Now, what we're trying to figure out is whether this is the same as sigma beta, sigma alpha. So let's just look at how they differ. Well, this part right here is symmetric in alpha and beta. So when I do sigma beta, sigma alpha, I'm going to get exactly the same thing. Okay? And here, I'm going to get the same thing, but switching the roles of alpha and beta. Okay? And so what I'm asking myself is, when are these two things equal to each other? Okay? But again, you see that most of it is already equal to each other. For example, the denominator is the same in both. The 4 is the same in both. This is the same in both. Alpha, beta, alpha, beta. And so really what I'm saying is that something times alpha is equal to something times beta for every choice of v. And so what I get is basically that alpha is a multiple of beta. There's one thing that could go wrong. The only way that I wouldn't be able to conclude that is if this number right here is 0. Because if this is 0, then these guys are automatically equal to each other. Okay? And so these are basically the two cases when sigma alpha and sigma beta commute. Okay? And so that's the proof. So these are some useful lemmas that we're going to use. Okay. Any questions about these proofs? Let me prove some other. So these are, you see, these are lemmas just about linear algebra, reflections, linear transformations, etc. So far, here there's nothing. I haven't at all mentioned the root system. Okay. So now let me give you some lemmas about the root system that we're going to use. Okay. So here's some things about the root system. Let's say that you take a root then we're going to show a bunch of things. First of all, that its inner product with itself is positive. Second of all, that when I look at the reflection with respect to beta, this isn't my group. we don't necessarily know this because this group is generated by the reflections with the simple roots. Now I'm taking an arbitrary root, and I want to show that that reflection is in the group. And the third thing I want to show, which we're used to already, is that if you have a root, then its negative is also a root. Okay? So we're going to show that. Okay. We know all of these things for the root systems that we have constructed so far, but we need to show it for an arbitrary root system that satisfies these properties. Okay. So that's, yeah? Question?
I'm sorry, I'm just not sure. What W are you referring to there? The one made from reflection?
So, right, so here I'm starting with a root system delta phi. And then from there, I'm constructing this, the group W generated by S. Okay. And so that's the W that I mean here. The second thing I want to show is just some easy fact about simple roots. That basically simple roots have negative inner product with each other. Okay. If these two guys are different, they're two different simple roots, then their inner product is negative. So if you think about this in the Euclidean case, what we're saying is that all the simple roots are at obtuse angles with each other. So let's prove these two lemmas. So first, let's do 1. So what does it mean to be a root? Well, by R4, by this fourth property, roots are exactly the things that you can get from the group by acting on the group, by acting by the group on a simple root. So let's do that. Let B equals W times some simple root. So, what is the inner product of beta and beta? I'm going to show these three things one at a time. Okay? So the inner product of beta and beta is the inner product of W alpha, W alpha. Okay? And I would like to now say that I can just get rid of W because W preserves the inner product. Why can I say that? To be a tiny bit careful. But the reason is that we know that these sigma alphas do preserve my inner product. Right? Reflections preserve the inner product, and my group W is generated by them. Right? What that means is that this element W is a product of reflections. Each reflection preserves the form, the inner product. And so that means that when I combine them, I still preserve the inner product. So these guys have the same inner product as alpha and alpha, which by R1 is positive. So that's the first one. Okay. Now for the second one, well, what's sigma beta? Sigma beta is the same thing as sigma sub W alpha, right? And I want to refer to my lemma over there, which tells me that sigma W alpha is W sigma alpha W inverse, right? Why? Because the assumption of that proposition is that W preserves the inner product. And I just told you why W preserves the inner product. So sigma W alpha is of this form, and these three things are all in the group. This is one of the generators of the group, and I assume that W was in the group. So that means that this is in the group. Okay. And finally, I have to prove that minus beta is a root. But with what I have done, it's very easy, because I can say, well, minus beta is simply the reflection of beta with respect to beta. Okay? And I just proved that this is in the group. Okay? So this is a group element acting on a simple root. Sorry, the group element acting on some root. So you're going to get some root. Okay? Because this is in W, and this is in phi. Okay? So that proves 1. Okay? Let's prove 2 now. 2 is pretty easy also, because all we have to do is say, okay, well, what is sigma alpha of beta? Sigma alpha of beta, by definition, is beta minus 2 inner product of alpha beta over alpha alpha alpha. Okay? Now, this is a group element acting on a simple root. So that means that this is one of the roots. Okay? So I have one of my roots, which is written as a linear combination of beta, which is a simple root, and alpha, which is a simple root. Okay? Now, I know that roots are either positive or negative. Either all the coefficients are positive or all of them are negative. The coefficient of beta is positive, right? And now, it's important to note that beta and alpha are not multiples of each other. And the reason are 3. So because beta and alpha are not multiples of each other, this is not just something times beta. This is a different direction. So these two terms are linearly independent. Okay? This coefficient is positive. That means that this coefficient has to be positive. This coefficient is positive, so that means that this number, or not negative. This number is non-negative, but the 2 is positive, alpha comma alpha is positive, the minus is negative, so that means that alpha comma beta has to be negative, which is what I wanted to show. Why could it not be equal to 0? It could be equal to 0. Yeah. This is less than or equal. Okay. So there's my proposition on some lemmas on root systems. Okay. So finally, with all these tools, let me prove another lemma on root systems. And then with this lemma, we're going to be ready to prove the main theorem that I went to prove, which is that W comma S is a Coxeter system. So my lemma says this. It says if alpha is a simple root, then the reflection sigma alpha permutes all the positive roots except for alpha. In other words, sigma alpha only sends alpha into a negative root. Everything else stays positive. Okay. Again, this is something that we know already for the root systems that we have encountered, but now we have to prove it using the axioms of a root system. Okay. And again, this is not hard from what we have done. Take beta in here, okay, and we just have to show that, basically we proved this already, we have to show that sigma alpha of beta is positive. But we kind of did that already. Well, not exactly. But again, what's the point? The point is that alpha is a simple root. Okay? Now, beta is not alpha, right? Which means that, beta is some root which can be written in some way as positive combination of roots. Right? Beta is positive, so that means that this is, a sum of positives times alpha I. This is bad notation, but you see what I mean. So the thing is, this thing already has non-negative coefficients. And you're only changing one of the coefficients, but this thing has terms that are not alpha, because beta is not a multiple of alpha. And so if this thing has positive coefficients that you cannot break by subtracting this, that means you have at least one positive coefficient in this expression. But you know that if you have one positive coefficient, then all the coefficients are positive. Okay. So this thing has at least one coefficient greater than 0, which is not leading alpha. So sigma alpha of beta is positive. Okay. And of course, sigma alpha of beta is not alpha, because the root that gets sent to alpha is negative alpha. So what I have shown is that if I have one root beta in here, and I apply sigma alpha to it, I get another root in here. Okay? And this process is reversible, because sigma alpha is an involution. So if I go from a root to sigma alpha times a root, then to get back, all I have to do is multiply by sigma alpha again, which means that this is actually a bijection. It's a permutation. Okay? So there's my lemma. Okay? And given this lemma, I think we're ready to prove my main theorem. And in fact, I don't think I need this anymore. And I don't think I need this anymore either, but let me leave it here just in case. Okay. So here's my main theorem for today. Well, it's not my theorem, of course. But here's the main theorem that we want to prove today, is that if we start with a root system, and we construct W and S in this way, as I described over there, what we get is a Coxeter group. Okay? So this is the main theorem for today, and this will follow from the following claim. let's think about this for a second. We're starting with a root system. We're constructing some group given by some set of generators. Okay? And we want to show that this group with this set of generators is a Coxeter group. Okay? Well, you guys have taken half of a Coxeter group class already. So how would you prove that something is a Coxeter group? This is a test. I'm not going to continue until you tell me. How do you prove something is a Coxeter group? You prove that it has the exchange property or the deletion property. So our favorite tools for doing this, and so what I'm going to do is exactly that. I'm going to prove that this thing has the exchange property. So what does the exchange property say? It says that if you take some group element and some reduced expression for it, and leave space for a 1 here. But what does the exchange property say? It says that if you multiply W by some sigma alpha, and you get shorter by doing that, where sigma alpha is one of the generators of the group, then you can write W as some subword of this one. So is this, I guess this is deletion, not exchange. Right? It's exchange? Yeah, deletion, yeah. This is exchange. It's exactly exchange. W is obtained by just deleting one of the letters. In here. Okay? But I'm gonna say something else here. So I'm starting with W reduced. I'm starting with a simple root, which, of course, simple roots correspond to generators. Okay? So this is equivalent to saying that you're taking sigma alpha in S. Okay? And I want to say the following are equivalent. What do you think I'm going to put here? What is this equivalent to? I mean, how do you tell me this in terms of the geometry? This is an algebraic fact about length in the group, but we know that we can translate that to the root system. The way we do that is we say that W takes alpha and makes it negative. But again, you have to be careful because we proved this equivalence for the root systems that we constructed from a Coxeter group. We haven't proved this for abstract root systems in the way that I have defined them on Monday. Okay? And so we have to prove this equivalence again for this definition of root system, which is more general. Okay? So here is my claim. Okay? And the point is that 2 goes to 3 is the exchange lemma, is the exchange property. And then we can use Matsumoto's theorem that tells us if you check the exchange property, you know you're a Coxeter group. Okay. So once I prove this claim, I will have proved my theorem. Okay. So let's prove the claim. So let me start by doing the direction from 1 to 3. Okay? So suppose that W alpha is negative, but alpha being a simple root is positive. Okay? Now what is W? W is sigma 1 up to sigma n alpha. Okay? So what I want to do is consider all of the other. I'm going to start with alpha, then consider sigma n of alpha, then sigma n minus 1, sigma n of alpha, etc. Okay? The point is that this one is negative, and at some point I reach a positive one. Okay? And so let me, at some point there must be a transition from sigma I plus 1 up to sigma n of alpha negative to the next one being positive. For some I. This must be true, right? Because I went from being positive to being negative, so let me take the I where that happened. There might be different choices for I, and if there are, I just take one choice. Okay? Now,
the longer one should be negative.
That's right. That's right. This one is the longer one. This one is the shorter one. So this should look the opposite way. So the longer one is negative. The shorter one is positive. Okay. But this is a setup that we like very much. Because, sorry, I forgot the alpha also. This is a setup that we like very much because what we have here is some positive root which all of a sudden became negative when I applied sigma I to it. Okay? And now you see why I wanted to prove this lemma. Because this lemma tells me what we're used to knowing, which is that the only root that goes from positive to negative when I apply the simple reflection sigma I is alpha I. Okay? So I get that sigma I plus 1 up to sigma n of alpha has to be alpha I. Okay. So now let me solve for alpha. What I get is that alpha is sigma n up to sigma I plus 1 of alpha I. Okay. And now I realize that I did need what I erased over there, because what I want to say now is, here's some vector, which is given by a group element times a simple root. Okay? And that means that we know that there is a corresponding reflection here, sigma alpha. And the corresponding reflection is given by, this is W, alpha I, W inverse. Okay? W, then sigma I, which is the reflection corresponding to this, and then W inverse, which is just obtained by reversing the word. Okay? So here I'm using the first part of that proposition that I had written up on that board. Okay? So that is sigma alpha. And think I wrote this incorrectly, right? I wrote this incorrectly because I want that if I multiply W by sigma alpha and I become shorter, what I want to say is basically that W can, a word for W can be obtained by putting sigma alpha at the end and exchanging it with some sigma I. That's why I was confused in calling this deletion, because I had it wrong. The reason it's called the exchange property is because we're saying if you multiply by sigma alpha and you get shorter, that means basically that you get a different word for W by exchanging a sigma alpha at the end for some sigma I. That's what the exchange lemma actually says, the exchange property. And now I want to show that W is equal to this, but I know what W is, I know what these guys are, and now I have an expression for sigma alpha. Okay? So I need to check whether W is equal to sigma 1 up to sigma I is missing up to sigma n, and then this thing, sigma n up to sigma I plus 1, then sigma I, and sigma I plus 1, and sigma n. I need to check that this equality holds. And we're experts at this kind of equality, right? We know that basically all of these guys from I plus 1 up to n cancel all of these guys from n up to I plus 1. And then this sigma I takes the spot of the missing spot that it should be taking. And so the right-hand side is just sigma 1. Then sigma I appears all of a sudden, and then I get sigma n. And this is true. This is the definition of W. Okay. So starting from 1, I got to 3. Okay. So that's my first direction. Now, let me do the second direction here. So this is 1 goes to 3. Now let me prove that 3 implies 2. So this is easy because you're assuming that W looks like that. You're assuming that W is given by sigma 1 up to sigma I is missing, sigma n, sigma alpha. And you want to show that W sigma alpha is shorter than W. And so this is pretty straightforward, right? Here's W sigma alpha. You compute it, you see that it's just sigma 1 up to sigma I, up to sigma n. And what you did is that you just found a word of length n minus 1 for W sigma alpha, where we assume that that word over there was reduced. So W actually has length equal to n, and this has length less than n. Easy. So that proves that 3 implies 2. And finally, let's prove what are we missing? We're missing 2 implies 1. Okay. So let's prove that not 1 implies not 2. The contrapositive. So not 1. If W times alpha is not negative, that means it's positive. It would be very bad form in like an Algebra 1 class to say that if it's not negative, it's positive. But here we're justified in saying that because we know that roots are either negative or positive. So the negation of this really is that you're positive. So I'm assuming not 1, and that means that W alpha is positive. That means that W times minus alpha is negative. And minus alpha is what you obtain when you reflect alpha using sigma alpha. Okay? So I get this, and now I say, look, I have exactly the condition of 1, except that instead of W, I have W sigma alpha. Okay? Now, what I'm going to do is now apply the direction 1 implies 2. You want to be careful and make sure that we proved that direction already. But we did prove that direction because we proved that 1 implies 3. We proved that 3 implies 2, which means that we're allowed to use 1 implies 2. Okay? 1 implies 2. If you have some group element times alpha being negative, then, which is exactly what we have here, then you can conclude that the length of that group element times sigma alpha is less than the length of that group element. You see, I'm applying 1 implies 2, but I'm not applying it for W. I'm applying it for this thing. Okay. And so what I just proved is that the length of W sigma alpha is bigger than the length of W. Okay? Which again is exactly the negation of this, because in this situation these guys do have different length. Okay? So the negation of this thing being less than is this thing being greater than. So I just proved not 2. Okay? And so you see that really the work was done in the step 1 implies 3, and then everything else just kind of follows from that. Okay? And there it is. There you have it. There's our wonderful theorem. And this theorem should give you some peace of mind. It basically tells you that now we can prove things about Coxeter groups, we can prove things about root systems, and basically we're proving the same things, because if I prove a theorem about a root system, then there's an associated Coxeter group. And we already knew that if we had a Coxeter group, then there was a root system associated to it. Okay? And so the theory of Coxeter groups and the theory of root systems are almost the same. I warned you that this is not a bijection, because we know that there might be different root systems for the same Coxeter group. For example, remember that the root systems that we initially constructed, all the roots had length 1. And these guys don't necessarily have to have length 1. But the point is that these theorems tell you that the connection is close enough that you can prove things about one and you get facts about the other one. And you'll see how useful this is. We're going to really exploit this. Okay? All right. Any questions? I have office hours now also. If you have questions that you want to ask there.
13 minutes. I mean, that's how I think of the computer.
How much is the battery then?
The battery and the charger together were $180. I think the charger was $20. I'm going to look at Zoe call, see if she wants to talk about Lemmas. You want to head outside real
They're in
quick?
my car.
Oh, I have to remember.
In the bag in my car.
Alright, Amanda, absinthe is really expensive. I guess being legal and being cheap are two distinct things.